Pluto is a far-off and covert, more unassuming planet that was once a piece of our close planetary gathering. However, recent declarations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a stunning discovery. They suggested that this cold world is on a potential crash course with Neptune. But how could this actually happen, and what might be the consequences of such a significant event? Are we witnessing an intriguing cosmic phenomenon, or is there more to this looming celestial mishap? Join us as we analyze the scientific consequences of a potential Pluto-Neptune collision. Pluto, a former planet that was reclassified as a dwarf planet, remains a subject of interest and study within the astronomical community. According to recent estimates by leading experts, Pluto's orbit is alarmingly close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising alarms about a potential dangerous collision between these two celestial bodies, which could pose a considerable threat to Earth. But how is such an event even possible? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It takes an astonishing 248 years to complete a single orbit. Since its discovery in 1930, it hasn't even completed one full revolution. However, the intrigue doesn't stop there. Pluto's orbit is marked by its unusually elliptical shape, deviating significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more extraordinary is its inclination, tilted at 17 degrees to the ecliptic plane. The way Pluto navigates its path is far more extreme compared to other planets. This inclination and eccentricity add layers of complexity to its orbital pattern. One of the most fascinating aspects of Pluto's orbit is its crossing point with Neptune's. For nearly 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, challenging our expectations of their positions in the solar system. This leads to the inevitable question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers tried to understand its unique trajectory. Unlike other planets whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stands out with its steep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit indeed crosses Neptune's. The stability of Pluto's orbit amid these complexities is a testament to the intricacies of celestial mechanics. The three-body problem in space involves predicting how three objects, like Pluto, Neptune, and the Sun, move and interact with each other's gravity. It's akin to predicting their future paths based on where they started and how they gravitationally influence one another. For Pluto, this problem demonstrates how its orbit, Neptune's orbit, and the Sun's gravity all work together in a complex manner. Terms like non-synchronous libration, orbital precession, and the VZK oscillation are critical to solving this puzzle. According to astrophysicists, what keeps all planets in their orbits is non-synchronous libration. In Pluto and Neptune's case, this term means that whenever Pluto crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from intersecting. Orbital precession, on the other hand, refers to the vertical movement of a body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned far above their orbital plane, providing an additional layer of protection from potential collisions. Another critical aspect is the VZK oscillation, named after three researchers, Vashkovsky, Zeldovic, and Kuzmin, who studied how objects move in space. It involves the gravitational pull between three objects, like Pluto, Neptune, and the Sun. For Pluto, this oscillation explains why its orbit near the Sun is so peculiar. Despite appearing chaotic, this oscillation helps maintain Pluto's stable motion over long periods. It highlights how space, though seemingly unpredictable, follows patterns and rules that keep celestial objects in order. These factors help stabilize Pluto's orbit, ensuring it doesn't collide with Neptune or veer off course. Understanding this three-body problem is key to comprehending how orbits evolve due to the gravitational interplay of celestial objects. This research sheds light on Pluto, our solar system, and even distant worlds and their stars. Mathematical simulations in the late 1980s revealed that despite its stable properties, Pluto's orbit is highly sensitive, with minor deviations in initial conditions leading to significant differences over millennia. However, these unusual orbital characteristics maintain stability over incredibly long timescales, effectively keeping chaos in check. Later automated studies have shown how the giant planets, like Neptune, Jupiter, and Saturn, affect Pluto's orbit around the Sun. Neptune has a remarkable relationship with Pluto. For every 2 orbits Pluto makes around the Sun, Neptune completes 3. This resonance helps keep Pluto's orbit stable. However, Neptune isn't the only player. Jupiter's gravity also plays a massive role in stabilizing Pluto's trajectory, as does Saturn's influence. Together, these giants ensure that Pluto continues its safe journey through space without running into trouble. These phenomena are essential for maintaining order and stability in space. Without them, the solar system would be a far more chaotic place. Bodies like Pluto could collide with others or be ejected from their orbits, triggering a chain reaction among other celestial bodies. For Pluto, especially with discussions about its potential collision with Neptune, understanding its orbit is crucial. It provides a clearer picture of the dynamic nature of our solar system. The case of Pluto demonstrates how even the most seemingly unstable orbits can achieve a state of harmony through the intricate interplay of gravitational forces and orbital mechanics. It underscores the importance of continuous observation and analysis to better understand our place in the universe. Exploring the depths of space often forces us to confront the strange nature of celestial bodies, and Pluto's orbit is a perfect example of this unpredictability. The concept of orbital chaos, which refers to the delicate dependence of a celestial body's orbit on its initial conditions, is clearly illustrated in Pluto's case. Even slight changes in the dwarf planet's position or speed can significantly alter its long-term orbit. Automated simulations have been immensely helpful in understanding how Pluto moves in space. These simulations use complex mathematics to model how Pluto and other celestial bodies like Neptune interact gravitationally. By tweaking small details, scientists can see how even tiny changes can dramatically affect Pluto's trajectory. Simulations from the late 1980s revealed a fascinating truth about Pluto's orbit. Despite its stability mechanisms, like non-synchronous libration and orbital precession, its orbit can still be irregular and unpredictable. Starting with even a slight difference in Pluto's initial position or speed can result in a vastly different orbit after a few years. Yet, even amidst this apparent chaos, Pluto's orbit remains stable over extraordinarily long periods, like billions of years. They include rough circles like Pluto's. This is a gigantic test. The intrinsic flightiness of these frameworks implies that drawn-out expectations are frequently loaded up with vulnerabilities. While mathematical models provide amazing assets for understanding and foreseeing the future ways of divine bodies, they also highlight the restrictions of our prescient capacities. These models rely heavily upon the exactness of starting circumstances, and any small error or distortion can lead to vastly different outcomes, making exact estimates an overwhelming task. Additionally, the tempestuous nature of planetary circles like Pluto's reminds us of the ever-changing and dynamic universe. While we've made tremendous strides in understanding space, Pluto's case reminds us how much our knowledge of the universe still remains limited. Understanding the gravitational effects of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It demonstrates that the presence and position of each planet can significantly influence the stability and trajectory of other bodies within the system. So why are leading astrophysicists recently raising concerns about a potential collision between Pluto and Neptune? Despite the complex forces working to prevent such an event, Neil deGrasse Tyson, a prominent astrophysicist and key figure in popularizing cosmology, offers a unique perspective on the mysteries of our solar system, particularly the fascinating case of Pluto. Tyson, known for his role in renaming Pluto from a planet to a dwarf planet, provides thoughtful analysis on the evolving nature of celestial mechanics and the public's interest in the overlooked realms of space. Tyson's stance on Pluto's renaming is based on the ever-expanding knowledge of our solar system. He sees the renaming not as a diminishment but as an essential adjustment to our growing understanding of the many bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of continuous learning and adaptation. He views the complexities of orbits like Pluto's as a reminder of how much there is still to discover about space. The curiosity surrounding these questions keeps the exploration of space so exciting. However, despite Tyson's optimism, his thoughts on Pluto's potential crash with Neptune paint a different picture. His concerns about the future of Pluto's orbits suggest that we may still have many secrets to uncover. Will Pluto collide with Neptune, or is this merely another moment of confusion in the constantly changing universe of space? Only time and further investigation will tell. For now, we are left with a deeper curiosity about how little we still know about our own solar system. We continue to study these celestial phenomena in the hope of uncovering more of the mysteries that lie beyond. The possibility of a Pluto-Neptune collision raises fascinating questions about the dynamics of the solar system, challenging traditional understandings of planetary stability. That two celestial bodies with such vastly different characteristics could collide is both troubling and intriguing, especially considering the current relative stability of their orbits. Given that Pluto is situated in the outer reaches of the solar system, far from the major planets, and Neptune is a gas giant with a strong gravitational field, the implications of such a collision would be enormous for our understanding of gravitational interactions and the evolution of the solar system. To comprehend the dynamics of a potential impact, one must first consider the structure and properties of the two planets. Pluto, despite being a dwarf planet, contains various elements and compounds believed to exist in a frozen state due to the extreme cold of the outer solar system. Its surface is covered in nitrogen ice, and it has an atmosphere composed primarily of nitrogen, methane, and carbon monoxide. In contrast, Neptune, a giant gas planet, is composed mostly of hydrogen, helium, and other lighter elements, with a deep, dense atmosphere. A collision between such disparate bodies would profoundly affect their structure and behavior, potentially creating an event visible across vast distances. What makes this hypothetical collision particularly interesting is the influence of other planets and bodies in the solar system. While Neptune's gravity plays a dominant role in stabilizing Pluto's orbit, it